So many thanks, Manish, for explaining this chemistry in such a simple way. Yeah. So we will continue the discussion on the chemistry part today. Today we thought about to bring some aspect of the chemistry, and Ravi is coming, and then he will discuss some other process to quantify the weathering rate from the landscape. And whenever landscape evolve, it is the physical process and chemical process both operates on the surface, and that's how we get the different kind of surfaces are there. So in the second talk of in the next 1 hour, we will have the talk, and after that we will have a lunch break. And then after lunch break, some of you have shown the interest to visit the library. So after lunch, I have discussed with our librarian, and then they will be here to guide their trip. And after half an hour, or maybe so after half an hour, we will start the lab visit things, and then. So around 3 o'clock we will start the lab visit. Maybe in half an hour we will finish that part. So it is not compulsory sort of thing. So whoever interested, they can join. I have already received those numbers. And then second half is free now. I mean, take rest. That part. One more announcement that earlier we made that announcement that we made a group, and then suggested that every day that group will write notes and then club the notes. The aim was that every day that group of 4 or 5 people will write notes, and then in the end of the conference we will merge all the notes and then share with all of you, because once you will leave, then the memory fades and then you may not be able to write. So this day, I mean, all of you should also work that whatever work has been left out in terms of the compilation note, you should compile, and at least tomorrow then you can send. So all groups will send the notes of all days, and then we will club all those things, and then later on it will be shared. So that's all the thing. So I invite uh, Mr. Ravi Kant Prasad. Ravi is working on the weathering processes, and I requested him to discuss about uh, the methodology to compute this part. So the qualitatively, there's lots of work has been done, but the main thing is come in terms of the quantification, how to measure the rate, and once the rates are there, then how to interpret the data for the landscape characteristics, and the landscape degradation part is there. So Ravi, I mean, you can start about this process part, and then basic of the weathering has already been discussed, and then.
Uh, oh, thank you so much. Okay, I know many of you are very hungry, so I will try my best to make it concise because this talk was actually scheduled for the your thing. This talk was actually scheduled for the evening talk, which is supposed to be relaxing. But here we are tense, we are hungry, and we are concentrating on PPT. So I will try my best to concise it as possible. So most of the thing I think Manish sir has told. So chemical rock weathering, why it is important and how we quantify. Basically, the quantification process I will be more focusing on this. So so basically, that talk I prepared for that timing that it will be in the evening, so I will go and relax the people. But somehow I will say something. But yes, to begin with, here is the solar system and here is our Earth, where only life exists. So you can say that what is the reason behind that only Earth has life. You can say why it is. Yeah, we have water. We have one possible reason one can say that okay, this is the optimum distance from the sun. If you go far, no life. Go below, near, no life. But you know, Earth has life since after Archean. It has life since then. So how it is possible? Earth, sun luminescence also increased by that time. but still Earth maintained somehow life. So why Earth has maintained? What is the reason behind it? And that is what, that it has atmosphere and it has carbon dioxide there, and that why we are concerned about this carbon dioxide, because this carbon dioxide is very crucial to maintain the temperature of the Earth. If it is high, somehow the Earth has tendency to make it low, and if it is low, somehow the Earth has tendency to make it high. So this is what the carbon dioxide. I am not going in detail. Everybody knows this. That is a greenhouse gas, which basically what it does is, when low wavelength ray from the sun, and when it goes above, it is a high wavelength, and it is the tendency of greenhouse gas is that it will absorb that heat, and that is how it maintains the temperature. The crucial thing is what is the percentage of carbon dioxide in the atmosphere. If it is high carbon dioxide, what will happen? It will absorb more heat, and the earth will warm. And if it is less carbon dioxide, what will happen? The Earth's temperature will go down. That is what happened throughout the geological history. We have found out that it has ice ages, it has warmer periods. So this is how the CO2 is very important. And where my topic lies is, I will give you a little bit idea that what is the carbon budget in our Earth. You can see that atmosphere has 600 gigatons of carbon dioxide, or you can say carbon, but most of the carbon is captured in these rocks in Earth. Most of the carbon is stored in the rocks and sediments below the Earth, and not in the atmosphere. Thank God. If it is in the atmosphere, all the carbon, temperature will be very high, like in Venus. You know, Venus, it is a 99% carbon dioxide there, and the temperature is 400 degrees centigrade, 600 degrees centigrade, like that. So somehow Earth have such mechanism to maintain the carbon dioxide in the system, and this is how that I am not going in detail, but what you can see that the exchange of carbon dioxide or carbon is more in those reservoirs which are less, like here 610, 600, and here you can see the transfer rate is very more. But when you see that where the carbon storage is very high, where you will see that there is very less tendency to exchange, very less tendency to exchange from one reservoir to another. So this is how, if we increase the carbon here, there will be more exchange, and this will definitely impact our Earth atmosphere. This thing I think Manish sir already explained, that rock weathering is important. It is a basically natural CO2 balancing. I can say that if carbon dioxide is balanced in the atmosphere, then only the temperature gets balanced. So this is how the reaction. I think I am not going in detail in this, but what basically happens is, here it is a carbon cycle, where what happens, you see this is the what silicate weathering happens, carbonate weathering, and this whole thing goes with the river and mixed into the ocean, and where what happens, that carbonate gets precipitated, and this carbonate gets, you see this is a layer of carbonate in the ocean floor. So what will it get subjected, and then what happens, remelted, and then again carbon dioxide comes into the atmosphere, and this is how the a global CO2 cycle, one of the global CO2 cycles is like this. So we talk about in the most thing is that you have to know that how this thing, how the Earth has throughout this geological history maintained this known as Earth thermostat. So here, this is what is called negative feedback. Everybody knows because we are all geomorphologists. Negative feedback says that whatever is the cause, the system itself tries to moderate that cause. If it is increase that cause, that is called positive feedback. But here what happens, you can see the first scenario over here. Warmer climate, temperature is high. Of course, if it is the temperature, endothermic reaction, this is what reaction, when you increase the temperature, reaction will be more. So what will happen? It will increase temperature, precipitation, vegetation, and that will increase to the increased chemical weathering. And what will happen? If increase chemical weathering, more CO2 will be consumed. If the reaction is more faster, then it will consume more CO2. And what will happen if it will consume more CO2? It will reduce that warmer scenario of the climate. So this is the first case where it reduces the cost. And the same way in the colder climate, what will happen? Cold, everything is cold, decrease temperature, precipitation, vegetation. So chemical weathering will decrease. If chemical weathering will decrease CO2 removal, and that will lead to the reduction. So basically, it will warming the basically the it will moderate this type of condition. So this thing happens throughout the geological. I have shown in from maybe 800 kilo year to here, but you will find throughout geological history from Precambrian or to this Holocene, this carbon dioxide has been fluctuated like this. When it is higher, it is a interglacial period. When it is lower, it is a glacial period, and like that. I'm not talking much about this because this is what happening in nowadays. But CO2 concentration has very much increased. That is around 400 ppm, which is supposed to be 0.03% or 300 ppm in the pre-glacial history. So basically, for the geological time history, we are basically concerned about this time interval. And now the more focus in this because due to the intrusion of Anthropocene, we can discuss it later on also. So let me give you some another perspective that why rock weathering it is important to study. Is very well known that rock weathering, what will happen? The reaction turns the parent rock to clay. If it is clay, then what is it is a basic character of a soil. So it is important to the soil formation. So we need to study the rock weathering, and it's very important. Rock weathering also what it does, and this is how we sampled in a field that we have to go from different layers and see how much intensity of weathering has been occurred, means how much cations or how much cations has been moved from this bedrock to this above layer. And another thing is that rock weathering, what will happen? It disintegrates the mineral, basically disintegrates the rock. So what will happen? Rock weathering removes the material, and this is how, due to the weathering, we have also seen the landscape changes. So this was my introduction. Basically, you know very well all those things. So basically, what I am convincing is that rock weathering is also important. It is important to estimate the physical erosion or physical transportation or sediment transportation rate. In the same way, what is going to altered throughout this, and that is what chemical disintegration. It is also important to estimate that also because it will affect the global climate as well because it consumes the carbon dioxide. Let me give you, I think these equations are just a repetition of those slides. So this is what the silicate weathering, where you can see that this carbon dioxide from atmosphere and water, it basically combines with this and producing these ions which is basically transported by the river, and this is what the clay it converts. So basically this silicate rock, everybody knows, we are geology people, so how Bowen reaction series, how different minerals form from higher temperature to lower temperature, everybody knows. So I'm not going in detail. That basically the silicate weathering, what happens? It gives the clay and these ions which is transported by the river. What happens in the carbonate weathering? Carbonate dissolves with water and carbon dioxide, and it gives these ions which fully dissolve into water and transported by the river. There is no residue here. As sir said that there is no residue, it does dissolve. But here we find some product, that is what the soil or clay. And other thing is that evaporite, which is a salt. Salt is just salt, add into the water and it will just dissociate itself. So this is what happens. So in nature, when we go to the field, these major three types of reaction is going on. Either it will be a silicate weathering, carbonate weathering, evaporite weathering, and what we go there and we collect these things which is in the dissolved load. So basically, and what one important thing I would like to highlight is that this thing that you are seeing that here, carbonate weathering, what happens that calcium and bicarbonate is releasing into the river and goes into the ocean. And the same way, what happens in the ocean, this backward reaction goes. Means these things get converted into carbonate, which is in the layer of the ocean basin. And this thing, and it evolves the carbon dioxide. Means whatever it has consumed, it has been evolved. So there is in a long time period, in the residence time of geological time scale of, let's say, million year time scale, what you will find? You will find there is no contribution of carbonate weathering in carbon dioxide consumption, because whatever is utilized here, it has been evolved. But what happens to, you will see the silicate weathering here, 2 mole of carbon dioxide is used, but this thing, it will precipitate only 1 mole of carbon dioxide. So what will happen? What is happening here? Due to the silicate weathering, 1 mole of carbon dioxide gets consumed. So that is why important people are concerning more about silicate weathering, because silicate weathering is an important factor which consumes carbon dioxide, and not in the long time scale. But if we are talking about short time scale, say we 100 years or 1000 years time scale, we consider both as a characteristic for the absorption of carbon dioxide. So in short, this is what um, when we go to the river sampling or what. So this is how I have bifurcated all the ions which are coming from different sources. One thing, that is the rain or atmosphere. Another thing is the evaporite dissolution. So these are the things which are coming in the water, right? As I said in the previous reaction, these are the things which are coming throughout the water. So this is how the things are coming from silicate, carbonate, evaporite, atmosphere. So I am going and collect the water from here, which have all the contributions. It has silicate contribution, silicate reaction. So I have all 4 things at one place. Now what I have to do? I have to separate this out. How much is coming from silicate? How much is coming from carbonate, evaporite, and atmosphere? So there are different techniques by which we separate it, and that is what the main focus of it. Like Priyank has asked one question, that how they are dependent on temperature and runoff. People have studied in different water sets. Different water sets, they studied how the effect of temperature is going on in weathering reaction. And this is wow. I think everybody knows that. I mean, their 12th class or something, Arrhenius equation, or where the temperature effect of reaction. Basically, temperature, what it does, any rate, any equation which is suppose A to B, how we write rate like this, right? Rate is given like this: rate constant into reactant to some order. Maybe this n is nth order. It can be 0 order, 1 order, first order, second order, like that. So basically, what temperature do is it will change the rate constant. And this is what the Arrhenius equation said, that it is some constant e to the power minus E A upon T. So this is what. So what will happen? If K will increase, the rate will also increase. So this is what the experiment which says, that it depends on runoff, which is P, and it also depends on temperature. So this basically, this is the diagram. If you focus here, what will happen from temperature? You see from temperature graph and this weathering rate, it is increasing exponentially, but for the precipitation, it is linearly. So this is what this equation tells, that it is linearly correlated with precipitation, and it exponentially correlated with temperature. So this is the one aspect. So another thing is physical erosion. Like Virat also asked this question, that what will happen if physical erosion is more? What we can say about the chemical erosion? Here people have worked out this, that what will happen to the physical weathering if more, what will happen to chemical weathering. Physical weathering means disintegration of the material. If it is this much size, reduced to the smaller sizes, what will happen? This much block reduced to this much, many blocks. What will happen? The surface area which is here more surface area. If you add all the surface area, this area will be definitely bigger than this area, right? So what will happen? It will give more surfaces to react with the carbon dioxide and water, and that is why it increases. So there is a power equation which this Mellot et al. 2002 they have proposed, that how physical weathering rate and chemical weathering rate are correlated with each other. But in a sense, you can see that it is some kind of correlation or power law are there. For a small time scale or for a region, you can consider it is a linearly correlated. So this is one of the things which controls the rock weathering. Another thing is the vegetation. I think everybody knows that vegetation, what happens that several acids, humic acid get produced in the root, and that also weather the rock very much. So there are different controls of weathering. So my concern on this topic, I will just tell you that how to derive the chemical weathering rate of a region and what are the techniques we use and what are the, I have one case study of a Western Ghats river is flowing and west flowing that I will show you few of the results from there. So there are different work approach. The time is less, so I am not going in very much detail. But what I am going in detail is little bit of detail is that I am going to discuss the dissolved rod chemistry and how this will affect the and how we are going in the field. So here is the first thing is that we have to go to the field, and this is what we do. We go to the field, we collect samples. So here my supervisor is over here, and this is my colleague Santama. So what we go to the inside at the middle because we don't want to have some contribution from the coastal or maybe some river bank. So we go inside the river, we collect water from there, and this has some characteristics, and that we record on the field itself. So we have to be very cautious. You have to be measure your gloves, everything. Otherwise, salt coming from here will leach into the water, and you will get very high TDS. You have to be very cautious because this is chemistry. So this thing we measure pH, temperature, TDS, conductivity. These things you measure in field. This is the first aspect. This is the first beginning of the quantification of chemistry. Now, this thing we have measured in field. We bring that sample in lab. What we'll do first thing, alkalinity. We do alkalinity in the field itself, but sometimes situations are not like that. So what we do alkalinity in the alkalinity is the just how we measure. It's a titration. If you remember your 12th class chemistry titration, what we'll do it is a kind of acid-base reaction. So this is what H2CO3 is reacted with H plus and gives to bicarbonate H2CO3. So how much acid? Basically, I titrate with acid and this water. I add acid in the water. Some fixed molarity. I have known the acid, what acid on what molarity I am using into the water, and how much amount I am adding. In that case, we can use N1V1 equal to N2V2, and we can identify how much carbonate this bicarbonate is coming from this this river water. So now the next thing is that we have to filter it, and during filtration also you have to be very cautious. Why? Because it should not be of glass. Why? Why it should not be of glass? Glass has composition of silicon dioxide, right? Silica, Si. If glass have some water, if you analyze that glass means water, you will find some silica in it. So basically, we design in such a way that it is non-metallic and means not containing of silica at least. It is a plastic container. So we we basically filter it because we have to this suspended particle we have to remove it, and that is why we have to filter it. Then only we can measure in the field in the instrument. So the next thing when we filter it, what we'll do we measure the dissolved silica, how much silica is it has, and that is what the spectrophotometer does. Spectrophotometer basically used for the analysis of dissolved silica in it. So how it does it basically we have some reagent, we prepared the reagent, and we measure throughout the light. There is it has some, I think it is not quite visible, but it has a color, and with a fixed 810 nanometer of this wavelength, that particular signature of that complex, it gives some absorption because of that color, and that is how proportional to the dissolved silicate. So there is a calibration curve, like I don't know how many of you are connected with doing chemistry in lab. So you better know that we have to make some calibration of known concentration, and then we measure our samples to give where it lies. So this is the one how we quantify the leakage. The next thing is that we have to filter the filtered sample goes to four major ions like those ions which I have filled in the reaction, that these ions we have to measure. These are cations and anions, which are sodium, calcium, magnesium, and potassium. These are the major cations. And in anion, we have bicarbonate, the first one, which is very much significant, sulfate, and nitrate. So most of the time we get balance, like NiCb sir had told now, these all get balanced. The charge, you make it charge balance, you'll find it more or less 5%. So now, how it measures basically, it's called an instrument called as ion chromatography. Ion chromatography, you know ion chromatography, what it does? Okay, okay, sir. So basically, when we add it has some resin which absorbs the ions, and due to the difference in this retention time, different graphs are coming, like sodium, potassium, this type of graph is coming, and based on this area we measure the ion concentration. So this is how we know everything, what are the major ions and cations in it, what are the dissolved silicate. Now the approach is that we have to give how much coming from which sources. Like I have said, there are silicate contribution, carbonate contribution, evaporite contribution, and rain contribution. So there are different methods. Like Manish had told, that was a forward modeling, that we have some ratio which is predefined, and according to that we measure it. But there is one method also called inverse method, where we quantify these equations. These are the basically mass balance equations. So basically, what we do, that how much, so this F is the contribution from ith or ith n member. So there are different n members. I represent the n members. So this is what the mass balance equation, and how we are doing this. We have to do models for it. This is what the inverse model does. If you go to the detail, you have to go through this particular book, that is Tarantola book, Tarantola 2005. This is the inverse model theory. So I'm not going in detail because we have to be programmed. So this thing, what we do basically in here, this is what this slide will tell the everything story, that what it do. So here, from here we are collecting water, and it has, here I am collecting water, and it has contribution from rain, it has contribution from silicate weathering, it has contribution from carbonate weathering, and it has contribution from salt. So this is what this water have, all these four major contributions. We are subtracting the pollution or anthropogenic contribution, because if we add that also, because that will complex my model. Basically, we collect sample from those areas which are supposed to be of devoid from any anthropogenic activity. So what basically this inverse model is does, I am just giving you what it does basically. We have this all characteristics. We basically go and collect the rainwater sample also in the field. We measure it separately. So here are the rain characteristics. Here are the silicate characteristics. We go and collect the rock samples also in field. We go and analyze this chemistry also, and here is a different rocks have some mean and some standard deviation. So this is what we have measured separately. Carbonate, if there is any carbonate rock is there in the field, we measure it that also, and these are the end member value, which is called a priori, which we give to the model, right? And what does this inverse model do? It will give me the a posteriori, because as in nature, no weathering is congruent. If I am saying that everything get dissolved, it is not like that. Rock is not going to dissolve. Rock is, especially silicate, it will form clay, and some ions it will go to the river. So So that here it is very important to do the inverse modeling to basically precise how much value is coming from which end member. So this is what is very important, and this is the output of this model, and we use for the calculation of chemical weathering. This is the perhaps the last slide, or maybe if the I will go for the case study after that. So as I said, silicate it can it can contain calcium, magnesium, potassium, and sodium. This reacts with carbon dioxide and water, gives these ions. Like carbonate, only calcium and magnesium carbonate gives calcium and magnesium ions. So this is the reaction by which here you can see, I don't know whether it is black, but it is Q upon A, discharge upon area, upon this silicate weathering rate SILWR. I don't know whether it is visible or not. It is the addition of all these cations which are coming from this. So we have to add this all into multiplied by QIA. It will give me the silicate weathering rate. In the same way, carbonate weathering rate Q by A multiplied by these ions. These things we have separated out through the inverse modeling. So now carbon consumption rate, consumption rate, how we can tell? These are the carbon dioxide which has been consumed. So based on this, what you are seeing here is that here 1 mole of calcium is releasing. Just see the equation, and 2 mole of carbon dioxide is absorbing. So what I have to do for this reaction, how much carbon dioxide has been consumed? I have to multiply it into 2 so that I can tell. So here it is 2 times calcium, 2 times magnesium, because also 1 mole of calcium, 2 mole of carbon dioxide is consumed. So 2 times magnesium. But in case of calcium, potassium, and sodium, 2 mole of calcium, yeah, 2 mole of potassium, 2 mole of carbon dioxide. So it is 1:1 ratio. So just we have to add this. So this is how we calculate the carbon dioxide consumption. Just I am overviewing the case study. This is the one of the areas in Deccan basalt. Deccan basalt, you better know. This is the whole overview of the basalt in the world.
What is the unit of chemical weathering rate?
Yeah,
Like
it's a ton per kilometer square per year.
what? Ton,
Yeah, here it is normalized with
tons.
area.
Okay.
That's why it is called ton per kilometer square per year.
Okay.
So this thing we have to measure in ppm, basically milligram per liter. We have to we have to very cautiously do the unit measurement, because we are measuring in tons.
Okay.
And this is how the Q we can measure in various aspects, like curve number method, like SWOT method, which are based modules. So there are different methods to measure the Q.
So where did you use the in situ rocks chemistry here to estimate the chemical weathering rate?
Yes, see, this thing is coming from the dissolved load, like this the previous. Yes, here I am collecting water.
Yeah.
So this whole basin weathering rate is governed by this water. Whatever chemistry I have here, that will tell me the story of this whole basin. So I can tell this basin have this much ton per kilometer square per year weathering rate. So this catch. Likewise, I collect samples in another places, and that will tell the story of that particular catchment.
No, you said you have collected rainwater,
Yes.
rock.
Yes.
How did you use those information to estimate?
Yes,
Yeah.
that's what this is what the, I'm saying.
Oh, okay.
This is the rain chemistry, this is the silicate chemistry, this is what we measure in lab. We collect this sample, rainwater. If it is not available, we collect, somebody have reported rainwater chemistry. What is that around that area? So that is what my a priori values to the model. And now this model will give me the a positive, which is quite representative, that it is not congruent weathering. Everything is not like dissolving. So this ratio is different from this ratio. So this basically gives me best fit values to use to calculate the weathering rate.
Oh.
Actually,
Okay. Yeah.
so time is less. Otherwise, I will explain. This will take one lecture to. I can. Okay, no problem. So this is how the. Okay, coming to my. Okay. So this is the global basalt. Global basalt exposure, the bariatrip very large. So here it is the Deccan basalt, which is also very large exposure of Deccan basalt. So this is where my study area lies. It's a junction of west flowing and east flowing rivers. So this is how this is the study map. One is going eastward, another one is going westward. Ambika and Girna, these two catchments. The reason behind we study these two catchments is although the lithology wise it is basalt, but temperature or pressure, even climatic conditions quite different, which I will show in the and this is how we separate out the different samples from upstream to downstream. This is just my logic to separate out the logic, means separate out the samples from upstream to down. Basically, this upstream region is very much hilly terrain. So we uh, collected it as one, means it is upstream area have a different signature than downstream area. And this is the Arabian Sea where some sea salt or some saline water contributions are also coming. So that we have to separate out. So what I'm saying that it is important to study the, although the lithology is same, but the climatic conditions are different. You can see temperature is almost same because it is a tropical area. So you will find 32 to 40 degrees centigrade difference from here to here. This is the warmer interior Deccan. But if you see the rainfall, it has very much difference from here to here. You see it is a 200 centimeter per year in this area because this is what the orographic situations happens here due to this drainage divide. And here what you find is that very less semi-arid kind of condition. These two catchments which are adjacent have a drastically different rainfall condition, and that is why it is important to study the weathering rates in this area and what are the controlling factors. Coming to my results, this is I am going to, we are going to communicate. It is in communication. So just this is what we do first of all, that we plot the mixing plot, and this is what we can have an idea that if suppose suppose this sample, it may be somewhere in the field. This sample have contribution from this source, and this source. Carbonate is very high. So how much is coming from this? If it is a two end member mixing, everybody can calculate. Like end member mixing, we can take the distance and we can calculate. But if it is 2 or 3 or 4, how we separate out this thing? This is what the inverse modeling does. So I have a idea. I got an idea that yes, this much contribution. Suppose these are the upstream region. What you can say about this? This overlies in the Deccan basalt chemistry. So I can tell there, yes, these are upstream area. It must have the contribution of this particular green patch more as compared to this or this. So this gives me an idea that how much contribution from which end member based on the proximity of that particular sample from that particular end member. So this is what gives me first idea.
Sorry. So this is a in situ information. Like this data.
This is the rock chemistry based on
rock chemistry. Okay.
And this is the dissolved node. So we have end members, and these are the dissolved chemistry. So we can tell that where it goes, means how much contribution. Maybe we cannot tell about how much, but we can have an idea that which sample is contributed, or which sample goes from which end member, right? So this is what the preliminary idea we got. So now the fraction of basically different end members is calculated throughout the inverse model. So what it does is that it calculates the basically fractions of how much is say saline alkaline soil in my field, how much is carbonate, how much is basalt, and how much is rain. These all data I feed a priori values calculated. It gives me basically the fraction how much coming. You can see very clearly that in the upstream region, these red patches is very much. Red patches are what? Red patches are basalt. So basically these areas are very much contribution from the basalt. And as we go from downstream from here, and as we go from downstream from here to here, because this catchment is flowing there like that. So here you'll find a little bit change, and somewhere you'll find a very much high saline alkaline soil. So this sample basically tells that yes, there may be some saline alkaline exposure in that area. So this is how the things we quantify in a catchment scale or a sub-catchment scale. So now I just plotted the tributary basin.
Excuse me.
What are the-
Back. This map that you have generated, it is a using inverse method you generated.
Yes, this is the inverse map. Yeah, I have written here.
So okay, so carbonate. I didn't understand. This is a whole basaltic terrain, right?
But yes, that's what. If at all it is a basalt, it's the igneous rock, but not like that. What happens? There are some interstitial spaces where carbonate gets precipitated. What will happen? I am collecting the water samples from these channels, river bed channels. What happens due to semi-arid conditions? Somewhere you find that carbonate gets precipitated, and we get the carbonate signature there. So it is not like it is a pure basalt, so there is no contribution from other sources. There are contribution, and specifically if you see this saline alkaline soil, you will find that this salt contribution are more here in this area basically. Why? Because the contribution from the Arabian Sea, because it is the proximity to the Arabian Sea. So sea salt contribution is quite reflected over here. In the same way, here also different sources are coming. So this is what.
So when you go away from the, is it indicating that when you go away from the shore, the soil formation in the terrain is becoming
Yes,
less and
this
less?
will give me various information.
Okay.
This will give me where the carbon saline alkaline soil exposures are there, where we can say that these areas are basically reflected the carbon saline alkaline soil. So basically, the upstream area is quite pristine if you see the very much contribution from basalt rock. But if you go to the downstream, you will get different reflections. This is a theolytic basalt, which is if you see the Deccan basalt, it evolved. It has evolved in 65 million years ago. That was what KT bond is. So at that time, it evolved, and there are different flows. Yeah, theolytic means it has minerals of plagioclase, basically. So there is two types of basalt. If you might have read in your BSc MSc, that there is two. One is calc-alkaline, another one is fluid. So it has different. Basically, the difference in the mineral. Basalt is basalt. So basalt have different mineral composition. What is basalt? This is ultramafic rock, na? So it has olivine, it has plagioclase, the most major part, and pyroxene. This is what we said that these minerals are in a rock.
Is calcium? No, I'm asking it is calcium plagioclase or sodium plagioclase.
It can be both.
So, no, you're talking about this carbonate. So, can it be from this only? I mean, from basalt. This contribution, carbonate contribution.
See, what I'm saying that this basalt is basically from silicate only. This basalt is basically, you don't get confused with this basalt is as a basalt as a whole. This only for the silicate. I have written this basalt is for the silicate only. Silicate means it can be albite, it can be anorthite. Means it has all plagioclase. But don't confuse with carbonate. Carbonate has separate calcium. That is what the beauty of this inverse model, that it will separate out how much is coming from the carbonate and how much is coming from the silicate only. It will give the contribution from albite as well as anorthite.
So, this area you're saying this area have some exposure of carbonate
Yes.
rocks.
That is what I'm saying, that it is not like homogeneous. When we study the small scale basins, it will give you much various complexities. If we study a large basin, we assume the things. Most of the things we assume that this will be the thing, because we cannot go into the complexities. When we study the small scale basin, we can infer these complexities, and that is what the motive of the study of these basins.
Red balls here, the soil, red balls in between the Deccan trap, red balls, the Deccan traps, red ball horizons.
Red balls, yes. Red balls basically, see, this is what red balls is what? In the Deccan basalt,
Yeah, there are some.
red balls is basically the marker, right?
So this is soil, yeah.
So, see, this study is based on dissolved load chemistry. I can study, see, that's why I said that there are two methods to study the weathering rate. One is whatever is coming from the river, you collect and you analyze. This is how you get the result. If suppose I am going and study the weathering profile, I have various red balls layers are there. Above that, various laterites layers are there. Below that, I have source rock are there. So that study is basically saprolite, soil, and bedrock. That transition will give me different kind of study weathering rate. Basically, we can generate the soil weathering rate also of an area. That I am not going in detail here.
Yeah, I understand. But suppose you have collected a sample in a tributary,
Yes.
and that tributary has actually came from a basalt, red ball basalt in the surface. In that case, how will you take? There are red balls which are exposed in the surface.
Yes.
I don't know the drainage network whether
Yeah, yeah.
they have crossed or not. If this is the case, how did you take care the?
Suppose this tributary that we
Uh,
are talking. Okay. What you are talking about this tributary?
that suppose when it is coming from upstream to downstream,
Yes.
it might have crossed some red ball horizon.
Yes.
Let's say.
Definitely.
Then in
See,
that
the red ball, which is formed, so there are various things. We have to look into the catchment also, that what type of
whatever rocks are there.
river we are crossing, what type of rocks we are crossing.
Okay.
So normally it is basically what now means if we see the basalt, there are different flows
Yes.
like Busse,
Yes.
other flows.
Yeah.
It has definite chemistry of
Chemistry,
every
yes.
single basalt.
Correct.
So we have to identify what flows we are talking about.
Okay.
So we also did that. We do chemistry of strontium isotope.
Okay.
So strontium isotopes have different flows, have different signatures.
Yes.
So based on that, we identify the flow also.
Okay.
Which flow we are talking about decking.
Oh, okay.
So we give that model to that particular.
Oh, that's awesome.
So that
Yeah.
will give me more precise.
Yeah. Great.
So this is how you can see how much difference here it is. Means almost 4 to 5 times difference in total chemical weathering denudation rate. It is not like silicate weathering rate, but it is a total consumption rate. So there is a large difference in these two. And what I would like to highlight here is that hydrogeomorphic control.
Can you explain a little bit back? Yeah, what is so you have different denudation rate at different part.
Yes. Just catchment wise, this circle is representing how much weathering rate, means total weathering rate. So here you can see that this basin of west flowing river are very high compared to this, right? Now, based on that, I can correlate with the rainfall. I can correlate with the runoff, and there is one interesting plot is that after the threshold value, we'll get a very high weathering rate upper threshold value. So this is what one of the interesting observations we find, that after the threshold value of rainfall or after the threshold value of runoff, we have a very drastically change in the chemical weathering rate. So we can tell about the geomorphic control also, basically the rainfall and runoff control. And one more thing is that hydrogeomorphic control based on the how relief is contributing to the basalt weathering rate. This is the basalt weathering rate which I have told now. Basalt weathering rate Q by A factor is there. So Q by A is involved in it. But when we just contribute the contributing ions, there's a very good correlation with it. Why such thing happens? Because we have mixed the Q by A factor here. Q is already correlated with the this thing. Q is already correlated with the rainfall. So here what we find that yes, relief is very important factor to release these ions from different tributaries. Because in a way you can say that higher relief, what will happen?
More erosion.
More physical erosion. Yes, more erosion. More erosion, what will happen? More surface area will evolve. More surface area, what will happen? It will leach more. It will give more concentration to the dissolved. So this is what the signature we are finding. Okay, I have 10 less. So just to give you the spatial plot of different catchments, how the weathering rates in these sections are varying. And this is the mean value, 70 plus 1 is 28, 10 plus 10 kilometers. Here you can find drastically different values. So just to give you an idea of how throughout this Western Ghat, different people have analyzed different samples throughout this river, and what are the weathering rates they have reported. So this is our study area, this study. This is the Girna which is in blue, which is west going, east going. And this is east going, west going, which is having very high value. These red lines are basically the west going. Blue eye is basically east going. So you can see various, these two catchment are very drastically different. And this is how it is basically differing from different lithology. We are coming from here to here to here. Basically, these are basalt up to here, and then granite and granodiorite rocks to here, and then we have charnocritic and granitic rocks in this Kerala region. So there are different values we are referring. So it tells that not only not only just rainfall, but also the lithologies are having different signatures. This is just comparative view of the continental, Indian continental, of different rivers. And this is what this is the small catchment with our study area, and how it is related with the other. So, because this is a small study area, it will give me the higher signature. But if you see that Ganga river is very less, because area is quite high. Different lithologies it goes through it. This is just silicate weathering, it's not carbonate. This is silicate weathering weathering rate in different river catchments throughout India. So based on that, just we conclude that this taken basalt basically it is the average contribution in dissolved load. Taken basalt contribution is 60%, saline and 20 to 30%, minor carbonate 5 to 10%, and then is around 5 or less than 5%, which we got from the inverse method. And there is 5 to 6 times difference from these two catchments, mainly governed with the rainfall conditions. Because if you see the rainfall plot, it's quite correlated with the basin. So, and one thing, an interesting thing is that threshold value, rainfall and runoff. Up to this, after we go beyond this, there is a very drastical increase in the rates. Relief is also gives a positive contribution because we saw that it is enhancing the pixel weathering rate and hence weathering also. So this is what we conclude from this. We are hungry and we can go.
So further
in inverse method, basically you are segregating the silicate ion and the calcium ion, you are saying?
No, every ion.
Matlab, segregation is happening, you are getting the concentration of every ion.
Yes, I will just giving you one example. Suppose I have calcium. It has coming from silicate, it has coming from carbonate. It will not coming from evaporite, but suppose it is coming from other sources also. Suppose it is coming from anthropogenic also. I have these values, means I know that these end members what they are representing. Suppose in a mixing plot I showed now, these are the regions this particular end members are representing. My sample is around here, this particular. So I have an idea that how much contribution is coming from here, here, and here. So this is how for every ion, not for calcium only. For potassium, for magnesium. This is what the mass balance equation is not went into detail.
So basically it will tell the contribution also
Yes,
from
basically
where it
how
is
much
coming.
fraction alpha 1, alpha 2. If you see the equation now, it is like that. I will write only one equation. Calcium upon sodium river is basically alpha 1 calcium plus calcium upon sodium from silicate, alpha 2 calcium upon sodium from carbonate, plus alpha 3 calcium upon sodium from other sources like evaporite or any other sources, anthropogenic. So this is how the mass balance equation goes. For calcium also, for potassium also, for whatever ions you have.
So basically if the basalt you are having, if it contains the plagioclase, if it is containing the calcium content more
Yes,
plagioclase, it will tell the contribution of that.
It will reflect in here now. will reflect in silicate.
Okay. ठीक है.
Could you able to distinguish between silicate weathering rate and carbonate weathering rate? Is it possible? So what was the ratio?
I have just showed you the. This is what the silicate. Okay.
Is silicate, okay.
This is just silicate. I have not showed you carbon, but yes, we have segregated value for carbonate also. What we are more concerned was silicate. As I said, that for a geological time scale, silicate is more contributing towards carbon dioxide absorption. I have not shown all the data.
Okay. So this place, where is the Arabian Sea? This way or this way?
This river is flowing this way, and this river is flowing this way. This is the two basins attached. This is the adjacent catchment.
So Arabian Sea, this is west. Where is the west?
This is the upstream region.
Oh, there.
For
Okay,
both
sorry.
the catchment.
Okay,
This river is going this way. This river is going that way.
Okay. So what was the ratio of this silicate weathering and carbonate weathering? You said, did you say something?
Ratio. It means it's around. Carbonate weathering is more. Why? Because what happens? Carbonate is very easy. As I told now that equation. Yes. This here you see it is a quite slow reaction. This reaction, silicate weathering, but carbonate weathering is quite fast reaction, and dissolution is very fast. नमक को पानी में डालेंगे तुरंत घुल जाएगा. Carbonate is very fast. It is a fast and it is very fast. So there are different rates. We get more carbonate weathering rate in this catchment because even it is a less amount, but it dissolves very fast. So we will get high carbonate weathering rate as compared to silicate weathering.
My question.
Carbonate weathering rate around double.
Acha, double.
About double. I'm not giving you number right now, but it's around double.
Just show me this slide, please. Where denudation rate Ganga, you compare with the Ganga last one, before last. Yeah. So if you convert this, your said, what is this y-axis?
Y-axis is silicate weathering rate in terms of kilometers per year.
So is it possible to convert this thing into denudation rate like mm per year?
Yes. This is the area normalized. So you can give it in millimeter per year also.
So if you then, so what is the denudation rate mm per year from this basin?
You have to calculate this. These are having very high because this is area normalized means suppose this is what Deccan basalt and here it is Ganga river. So how much equal area?
Acha.
This is we are comparing.
So what is
we have area normalized. So this is what the value is. Because here you can see Ganga river basin is quite less.
Yeah.
Because we are considering 1 kilometer square area. How much?
So if you normalize with the area, so it is showing that Western Ghat is denuding very fast.
Yes,
Chemical.
It has basaltic rocks. In basaltic rock, it has such minerals which tends to erode very fast, which tends to weather very fast basically. These are quite reactive, olivine, paleogenous, because this form in the Bowen reactors very early. When it exposed to the surface, it will react very fast. Unlike the quartz which is at the last, won't react, very less. Quite reactive.
So it seems that chemical weathering is more, so it means denudation is more.
Yes, it is other way around also. What happens if chemical weathering of a exposure is more? It will basically break that rock also. So what will happen throughout slope? It will get more physical weather also. So there is a relation between that Millard paper that I showed you. That they have given a relation. Physical weathering is somehow some chemical weathering into some power being. So they have given some power law based on different catchments they study, basaltic rock, granitic rock, other catchment rock. So they come up with this relation. I showed in the
But as far as I know, if I calculate the denudation rate from Ganga plain, so it will be like 1 mm or 2 mm per year. As far as Deccan Trap is concerned, it is very, very less, right? Less than 1 mm. So how does fit here? I didn't understand this part.
What you are saying that chemical, you are talking about chemical weathering?
No, I'm talking about simple denudation rate.
Okay.
So
Only
is
denudation
it
when you are
comparable?
Physical denudation you are talking about, right? Or you can combine the chemical plus physical.
So I'm talking about.
That is what
I think I'm talking about the denudation rate which people have measured using this chemistry for Ganga, which will be around, I think, 1 to 2 mm per year. It will not more than that. But as far as this Deccan plain is concerned, this denudation is
more
very.
here.
But denudation will be really less, right? I don't know.
This chemical denudation we are saying it will be more here in Deccan Basin.
Okay.
Definitely it will be more. First step to do. But see, thing is that you are talking about chemical denudation. It will contain carbonate also, it will contain silicate also, it will contain other sources also. So that will then factor. I am comparing the silicate only. So that's what it is the difference. If I suppose I add the carbonate, this will go up because carbonate maybe exposure are there in Ganga basin. Lot of this area of valleys and there are lot of carbonate exposure.
But you okay?
In fact, people have reported that carbonate is main contributing in the Ganga basin. Carbonate, if you add this up, then you will compare, it will go up.
Yeah. Oh. Yes. Oh, density. Yeah.
Per year.
Then you can compare. Okay. You want to? Yeah. Yes. 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 So actually, so if we use, if you go by cosmetic data, then denudation in the Himalaya is 1 and 2 mm per year. And when I asked the Scientama, he was telling him that his data is like 0.04 mm per year.
That is physical.
So it's very less in case of Deccan.
Physical weathering, it depends on the rainfall conditions and other things. Because if you see the Deccan basalt, here the rainfall condition is quite high. But if you go the interior Deccan, rainfall condition is quite less. So there will be difference on that also.
Okay. Yeah. Acha. Hmm. Yes. Yes. Yeah. Yes. 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 Yeah. Thank you. Nice. Very nice.
You go first.
Thank you. Just because it is the Deccan area and you are saying a lot of carbonate weathering is there, any springs, any contribution from groundwater weathering? Is the groundwater chemistry different?
In Narmada catchment, I read one paper by Gupta et al. 2011.
So
They
could you
have reported some
segment
spring
that out?
samples.
Could you segment out groundwater chemistry or
Yes.
contribution from the river
In my
water?
area, I couldn't find any thermal springs, something like that.
And-
But in Narmada catchment, there are some reported thermal springs also. So there we have to give one more end member like thermal end member.
And does the river reach morphology have anything to do with the kind of chemistry the water is reporting, or was it all bedrock channels that you sampled?
Mostly there are
Bedrock samples. Okay, fine.
But in the downstream area, maybe in the west wing, this one over here, lot of clays, and these are basically the estuary region. But these all areas are basically the bedrock.
Interestingly, also your salinity increases both towards the Arabian Sea.
Yes.
And because you said tidal effect, fine, but it also increases inland, away from the divide.
That's what this. Yeah.
Is that aridity?
Yeah. This the salinity that you have must have seen.
Yeah. So it increases towards the left as well as towards the right.
Basically, because of the
tidal effect.
But here, what happens? This is the semi-arid catchment of the Deccan, where different type of saline alkaline soils also contributing to the dissolvent. So this is what we are having.
Thank you.
Sediment load present. So I think you are expecting the same result.
we are kind of doing mass balancing from the sediment also. See, whatever is coming from the dissolve,
Yeah.
that should
Come to
must
the come.
diminish from the sediment,
Yes.
whatever flowing.
Uh,
But we have done in our paper this, we have calculated the mass balances from the sediment also, that what we are getting balance or not. But there are so many uncertainties here because we are collecting sample in once in a while, maybe in monsoon season.
okay.
That will basically, and we are taking one sample only at one. Catchment have several heterogeneity.
Yes.
It depends on you how much depth you can go to the heterogeneity. So
But
normally, what we were saying that what will happen if we measure from the
yeah,
sediment?
yeah. What will happen?
It is quite lesser from what I get from the dissolved.
Okay.
It is around 5 to 6 times less of sediment when we calculate the mass balance.
Acha.
Compared to this. But they are highly correlated with each other. So
Okay.
this says that both theories are correct. Both
Yes.
models are correct because they are
Yeah.
correlated.
Uh,
But due to the heterogeneity, because our samples is one time representative, it cannot be representative for a whole
Yes,
basin.
yes, yes.
We are going to the field for one time sample. You have to calculate multiple samples so that you can come up with this mass balance. So dissolve as well.
okay. So this case study is very because of the one lithology. It become very easy. Suppose it is having a lot of different lithology.
Yes.
Will it be applicable there?
Yeah, that is what my second area
Okay.
study.
You can apply.
I have two area in Rajasthan.
Uh,
One is in Mount Abu and one is in Udaipur. What will happen in Mount Abu, if you see, that is basically Sirohi granite, which is granite and gneiss. And if you go to the Udaipur, lot of system lights, lithology.
yes, yes, yes.
One study I have not shown you.
Okay.
That study area is my second topic.
There
You are
also
saying that
yeah.
keeping the lithology different,
different.
and same climatic condition. In Rajasthan, almost same arid and semi-arid climates are there. So I am where I am keeping the climate constant and lithology variant. So I will definitely see the contribution of the silicate primary minerals.
Okay. And in conclusion, why you have not bring denudation by dividing the densities as suggested? Why you have not bring that point?
See,
if you divide, if you use this sediment a ton kilometer per year divided into density, then you will get the
I can show you
denudation.
both
So
millimeter per year. But for the most of the time people have reported from dissolved load they used to give like this.
Okay.
10 per kilometer per square meter. I can convert it into millimeter.
Yeah. Why I'm
I
saying
have to take care of the density.
yeah. So why I'm saying because
So-
my mind I think in terms of per year.
Yeah.
So it is difficult for me to convert this into per year.
Yeah. Because I have not correlated the physical here, physical weathering rate. If I compare the physical weathering rate with chemical weathering rate, then I have to keep the both units same.
So, yeah. Right.
Then you can able to-
Yes. Yeah.
Any question from the new person?
About that carbonate you are saying, in the Deccan Trap we have this early Deccan Trap flows also, and in the your area is lying in the like in the northern portion almost.
I'll give you what are the basically what flows it contains.
Okay. I'll just complete my question. So there are some of the basement which is in the evolution of Deccan Trap, some basements is contaminated, and there are some papers of the pre-crystalline genoliths.
Yes.
So that could be the possibility that you are saying this like we have the sim depositional or sim consolidational these things, the carbonate or the epi you are saying
Yes.
about, and some of these millerites are also there. There's like quaternary timing. So are these carbonates are from this like contamination of the this basement or something like that?
What I
Can it be?
say that
There are some papers by like Nitin Karmakar sir from Pune, because I am from Maharashtra and I studied this area all the time. So can it be that carbonate, the
yes,
earlier
I would
one?
say that people have reported many zeolite precipitation in the void structure, many carbonate precipitation in the breaks or in the tracks of this Deccan basalt, and that will reflect in my dissolved load also.
So is there any like method to like
Yeah,
classify
we
the
have
weathered earlier one and this recent one?
Yes, see, this plot is basically give you an idea that here what we did we have non-monsoon sampling also. So we wanted to see if something gets precipitated, it will signature in the non-monsoon season. So here, I'm glad that you asked this question. That here you will see that the monsoon season, which is the field color, but non-monsoon, which is open circle, what you will find, there is a decrease in calcium upon sodium value. So what will happen to the calcium in non-monsoon season? It gets precipitated in the soil. So this is what the signature I am getting from the non-monsoon signature. So this will give an idea that which region is showing me how much carbonate is going precipitated. So this is how I have plotted the non-monsoon and also the sodium addition on this. Here you will find that more because of the more sodium in the downstream region. I have to see that there are people who have reported the anthropogenic contribution also. The anthropogenic contribution have various challenges because there is not one source which is contributing to that.
Yes, yes.
There are some sewage,
Yeah.
there are some industries,
Yeah.
there may be some geology, pyrite or any other chemically. So we have to be very cautious that where is the main anthropogenic contribution is coming from. Like,
But we know that, like, we know the settlements are there.
okay, this is the beauty of inverse model. I am not giving that model a number. I am giving this thing. I am giving this thing. Mean value plus their value. So I am giving some number plus the error associated with that. So the model will take throughout this range and give me the best fit value. That okay, no, this is the best fit value. So this is so I have to give the anthropogenic and member also. So somehow we can calculate, but we have to check whether it is coming correctly or not, whether I will be able to explain it or not in that sense. So then we have to go rigorously to the field, observe these things. Anthropogenic. We have to take sample from sewage also to fix that.
Okay.
So that's why I have excluded those parts.
Okay, thank you.
For the upstream reason, there is very
Less
less
anthropogenic.
negligible anthropogenic.
Yeah, thank you, thank you.
Okay, yeah, many thanks, Ravi, yeah, for this excellent and interesting talk. And then, so we will finish it here. Just one thing I would like to highlight this part about the connectivity of whatever we had discussed earlier. So in the yesterday or day before yesterday, there was lots of talk about the erodibility and then how to bring this erodibility and the role of lithology in the landscape evolution system. And maybe this one slide which will highlight these things, that the understanding of the weathering process is also equally important. And to see these things, I mean, in general, it is considered that charnockite and gneissic, these are the harder rock, you will put the higher erodibility in the system, but it will also depend on what kind of climatic setting is there. And the rate of weathering of the basalt, which used to be considered highly weathered rock, you can see that its rate of weathering is significantly less than the charnockite and granite. So, so it may be possible because weathering rate will ultimately weaken the rock, and then erodibility may be different. So, so when you are doing this landscape evolution modeling, then looking for erodibility aspect, you have to also consider in which kind of climatic setting is there. And here, this is all right. This you will expect that yeah, that basalt will be highly weathered rock, and then you can look forward for the lower erodibility rock. But here, it may be possible in these cases that the erodibility of these rocks is higher than this kind of rock, where it is also basaltic. So, I mean, the working on the landscape is a very complex thing, and one by one, we will understand different kind of feedback in the systems. And that was also the aim, to bring the chemistry aspect is there. And if we look the famous book of Anderson, and Anderson, it is named as the physics and chemistry of the landscapes. So though in this workshop, there will not be much of the chemistry, but some of those things we have brought to highlight those things, that these are equally important whenever. So even though if you are working on the physical modeling of the processes part is there.